first, we will hear a talk from Oliver Schreer, who's a professor at the Fraunhofer Institute in Berlin. So I've had the pleasure of knowing Oliver for at least about best part of 2 years now, through a European project that we are work package leads on. And Oliver has extensive amount of experience on XR at a European level. So he was previously the PI for a consortium called XR for All. And the project that we are working on together now is called XR for Human. And the overarching theme around these projects is how to make these emerging immersive technologies accessible to the majority of society. So I think Oliver's going to be talking about some specific area within that today on volumetric video, which is the area of expertise in his laboratory in Berlin. And he'll tell us about the past, present, and future techniques. So I'll hand over to you, Oliver. So thank you.
Great. Thanks, Faisal, for this invitation. And welcome to this presentation. So I will guide you through a journey past the present and the future of volumetric video. But before,
is it not moving?
No.
Oh, technicians.
Okay.
You got it.
Okay. So, but before, I will briefly present myself. So I'm working at Fraunhofer Heinrich Hertz Institute since 1998, which is one of 75 Fraunhofer institutes in Germany. And Fraunhofer Society is the largest research organization in Europe. Shortly after my arrival at Fraunhofer HHI, I completed my PhD on stereo image processing. So I'm in this 3D topic since 1999, at least. I then started giving lectures at the Technical University Berlin, finished my habilitation degree, and since 2015 I'm heading, together with my colleague, a research group on immersive media communication. I did a lot of, during my career, did a lot of European projects. I also coordinated several projects. And as a follow-up of XR for All, the umbrella organization XR for Europe was founded 2 years ago, and I'm a member of the board of directors, bringing all stakeholders of XR together in Europe. So what are we doing in our department, Vision and Imaging Technologies? We do split it in 4 different research groups, dealing with different topics from capture to processing and interaction, cognitive systems, and so on. So if we look at the processing chain, we do research along the whole processing chain. We develop various capture systems. We do processing, modeling, and also work on the display side, and with some pretty nice demonstrators. And overall, interaction is also part of this research topics. So our research enters a wide range of applications, the whole area, whole spectrum, with a lot of things in multimedia, but now we also work in agriculture, industry, medical domain. And we have several core competences. So that's mainly in 3D reconstruction, reconstruction of humans, also synthesizing humans, tracking, scene understanding using various types of sensors, and also with the help of extended reality devices and technology. So these are some of the methodologies we're using. As you might imagine or might expect, AI enters the whole domain of computer vision. So we do now a lot of AI research, and so these are some keywords which we tackle in our research. The whole department has about 35 researchers, and so in the same amount of students. Yeah, but now let's dive into the topic, and let's climb the volumetric mountain. So here are some breakpoints on the way to the top, different subtopics which we need to pass to finally reach the top of the mountain to talk about the outlook of this technology. But first of all, we start with the question, what is volumetric video? So the aim is to represent real humans as natural as possible in a digital way, but not just as a static 3D model, but as a highly realistic dynamic 3D model. So this is usually done in the film industry and in gaming and so on by creating a character. Then some actors need to do some motion which is captured, and then with the given motion we are able to animate this character. But this has some drawbacks which are listed here. So some parts can hardly be tracked and also animated, such as facial expressions and dynamic behavior of clothes and so on. And high precision motion capture is also pretty complex. So therefore, we do something different. We capture the person with several cameras, and from the video information, we create a dynamic 3D model. So we end up with a sequence of meshes, and then in the render engine, we render the sequence of meshes and get the dynamic behavior of this 3D model. And the target is to do this in pretty high quality. So that's all about and this kind of media format we call volumetric video. So let's look back in the history, and here's some table with some milestones during the last 20 years, I would say, with different terms. Some of you know, perhaps, like virtual view synthesis, 3-viewpoint TV, 3-viewpoint video, performance capture, videogrammetry, and so on. And there are some milestones in years which present some of the systems which belong to these developments. And I will briefly wrap up some. So here is an example, very first example from Takeo Kanade. It was capturing of Super Bowl, and it was completely hardware based. So it was where 30 robotic cameras were mounted in the stadium, and then the virtual movement was just switched from one camera to another camera. But this required high precision steering of the cameras. So this was one of the very first examples for 3-viewpoint television, but completely hardware based. Yeah. So in late 90s of last century, we already worked on virtual view rendering for teleconferencing. So this is a project where we still developed hardware for depth estimation and so on. And then there were several other projects in the early 2000s where we looked into virtual eye contact to set up true real life size video communication systems. Some examples of demonstrators can be seen here on the right-hand side. You see how we solve the eye contact problem by creating a virtual camera. Then we further expanded our capture system and went over to full body capture. Here's an example for this telepresence wall. Several cameras mounted here. And then furthermore, the first attempts towards volumetric video started. So on the left-hand side was one of our first 23 camera systems in 2016. And on the right-hand side, you see the pretty well-known work from Microsoft in 2015, first volumetric reconstructions. Yeah, so this is a short snapshot about work in the past in this area. And let's talk a little bit more about volumetric capture. So there are several volumetric capture stages out there. We finished our very first prototype in 2017. But there are also 4D views and the former Microsoft mixed reality capture studios opened in this period. We spinned off a company which is called VoluCap with our technology. So this is considered as the second version of our prototype capture studio. Holograms in Ireland is also working on volumetric capture. And so there are a number of studios out there with different focus and different capabilities. You notice some of them are based on green screen. Here we use lit background to also create different lighting conditions, as you see on the picture in the center on top. But there are also other studios worldwide distributed in Asia. Intel studios are still listed here, but they closed already, and some other examples of mobile studios. And here is a map, which is from 2022, where you see the distribution of volumetric video capture studios today, worldwide and in Europe. And you see here, if you zoom in, two dots which belong to Fraunhofer HHI and VoluCap in Potsdam-Babelsberg. So there are quite a lot of studios. However, this is certainly not up to date because there were some issues in some of the studios. So, for example, Microsoft stopped their activities and shut down their studios because, the business type of expectations were not fulfilled. But still, some studios are still alive and find their niche to earn some money. We are in a pretty lucky situation because our system is completely research focused. Yeah, we fund our activities with research projects, so we are not do not require monthly income. Yeah, so that's good for us. Yeah, and this is our latest version of our studio because we moved 1 year ago. in a new facility, and we had the chance to revise our capture setup. So this is now much more flexible. We can mount cameras wherever we want. We can hang on additional cameras, additional lights, and so on. So it's much more flexible. And our researchers are pretty happy to have this capture system available to capture multi-view content for research. So if we look at different systems, they differ either in camera types, number of cameras, but also resolution. In our case, for example, we use 20 megapixel cameras, and as already mentioned, background is also different. Some of them belong to are based on green screen. Some of the studios work with lit background. Some do not have any constraints. So quite variation between all the different studios. But the objective of all of those is to create highly realistic, high quality, dynamic 3D content, 3D models of humans. So then let's have a look on the workflow of how we create volumetric video, how we do this. So here's a pretty rough diagram on the overall workflow, and you see here some distinctions. On top we have RGB, RGBD acquisition and followed by depth estimation, but we can also feed our data fusion with depth information already. So then we have this fused data, which then end up in a 3D point cloud, and then there are again different ways how to proceed. There is a point cloud based workflow out there, and mesh based workflow. In the mesh based workflow, we need to do the meshing and encoding. We are able to stream, and then finally we end up in our application and do the real-time decoding of our volumetric video, and finally render the volumetric assets. So if we look more on the mesh-based workflow, which is the workflow we are using, you see here again different processing steps. The blue one is on the capture side, where we do keying and depth estimation. And in our case, here you see some numbers. If we do our capturing for 1 minute, we start with raw data with an amount of 1.5 terabyte of raw data, which is a lot. But then along the workflow, we achieve a significant reduction of the data, and already the 3D point cloud is much more reduced in the range of 30 gigabytes. Then we do the meshing, we do mesh reduction. Again, we achieve reduction by 30 by a third to a third. And then if we encode our meshes and the textures with standard encoders, mesh encoders and video encoders, we end up with on about 600 megabytes per 1 minute of volumetric video, which is not that much. And this, we also developed our own MP4 container, which we can then also stream and import in our AR or VR application and render our volumetric assets. Yeah, this is some examples of the processing chain. So we start with individual depth maps from different cameras, different perspectives. We fuse the depth maps in a single common point cloud. Then we do the meshing. We reduce the mesh, and finally we texture the mesh and get our volumetric asset. There are different ways how to estimate depth from vision-based systems. So here that's stereo-based depth estimation workflow, which does surface region matching. So here we use spatial candidates and do a statistically guided update for comparison. The advantage with this is that we do not have any search ranges and so on. It's nicely fits on GPUs, so we can do pretty fast, high quality, high resolution depth estimation. But we also started with learning-based approaches. And this is an example of recent work. So this is some work published at BMVC. And but my colleague worked on top of this standard with MVSNet. And you can see that with learning-based depth estimation, you can significantly improve the quality. So this is our standard workflow, and you see there is some details missing in the fingers and so on. But on the right-hand side, our improved version has much more detail. So again, in this field, AI is pretty helpful and overcomes standard workflows. Point cloud fusion is an important aspect. So there we use the trunk TSDF to do the fusion, and with this we can extract the surface pretty nicely. And so after having this point cloud, we do the Poisson surface reconstruction to do the meshing. For sure, some smoothing is applied to clean the mesh afterwards, and quadratic edge collapse is used to simplify our meshes. Because you can imagine, if we have millions of 3D points, we also end up with millions of faces, and that's far too detailed. So therefore, at least in depending on the geometry of the object, we can concatenate various triangles and get a much more reduced 3D model. Yeah, another important aspect is texturing. So the challenge here is to create a texture map which contains all the texture in the high resolution. And the tricky thing is how to organize this texture map in a way that it's compact, but also selecting the right patches from the original views. So as we have different camera images of the same part of the object, we need to carefully select the patches, and also do some need to avoid edges between neighboring patches and so on. So that's a pretty interesting research topic, and various ways how to solve this problem. But finally, we end up with either 2K by 2K or 4K by 4K texture map, which is used to texture our 3D model. Yeah, as said, we also want to stream our volumetric assets. So therefore, we use standard encoders for to create an MP4 stream. So we have the mesh encoded. We use Google's Draco encoder. For video, we use our standard H.264, H.265 video encoders. And we also support audio because our captured humans also speak and talk. So therefore, synchronized audio is also important in our video stream. Yeah, so this is then packed in a multiplexed in an MP4 container and can be transmitted. There is one interesting aspect because where we also do so far the workflow does the whole mesh creation on a frame basis. So we need to do some temporal alignment of the meshes to avoid flickering and so on. So therefore we do temporal registration, we define keyframes, and then just use the same topology and just change the vertices. This leads to pretty smooth meshes over time. But if we do so, we also can save some amount of data because for a given mesh period, we only have the same topology, and we just transmit the 3D coordinates and associated 3D normal vectors. So texture coordinates and faces remain unchanged in this period, so this saves a little bit of data. But even more important, it leads to a pretty smooth and temporally consistent dynamic mesh sequence. Yeah, in the receiver side, we have a plugin which decodes our mesh and then does the rendering in the render engine, which is either Unity or Unreal. In our case, we mainly rely on Unity. So I mentioned already this other stream of point cloud representation. So there we also need some encoding of the point clouds, and this is one example. So in this case, the point cloud is projected to different planes, and these planes are then transmitted separately, the occupancy map, the depth map, and the texture. And this is then packed and encoded with standard video encoding and serves as the point cloud stream for video-based point cloud coding. There is also geometry-based point cloud coding out there. So here we represent the point cloud by an octree. And here we can achieve significant reduction. And there are different ways to encode this point clouds. So there are different ways out there to do point cloud coding. Here are some examples. One of our first production on the right-hand side, which is a young girl interacting with the virtual scene. So there is this rabbit walking by. She picks a real apple, bites in the apple, and then throws away. And as soon as the apple is flying, it becomes a virtual apple. Then we see the tiger shouting against the tiger. So this example on the left is also again already 5 years old, but it's pretty impressive because we have this moving clothes here, and you see the capabilities of this approach, which so this kind of motion can hardly be done by animation, yeah, by cloth animation. Yeah. So there are some other projects and examples. So here on the right-hand side, you see some AR example of our German TV anchorwoman, Linda Servakis, from the German news. So she's explaining the news in AR. You can invite her at home in the living room and get the news represented. These times, the cathedral in Paris disaster happened. Yeah, and then one use case is pretty important, and we work a lot on this because here volumetric video really becomes relevant, which is the preservation of memories from Holocaust survivors. So we were able to collaborate with 2 Holocaust survivors in the past 3 years. One was Ernst Grube, and we recorded him in at Volucap studio and recorded about 50 minutes of volumetric video. And this is split in 5 episodes, and Ernst Grube is telling his memories, what he experienced during the Nazi regime and his time in Theresienstadt, the concentration camp in Theresienstadt, and the liberation. So it's a pretty impressive and experience, and it's considered as the longest VR experience using volumetric video. We also did a second project with Eva Umlauf, which is she's considered as one of the youngest survivors of Auschwitz. She was 3 years old when she was liberated. Yeah, here's an example of this experience, short snapshot. So in this experience, he's talking with telling his memories to a young student, and you as a user are standing in or are in this scenery and observing both while Ernst Grube is telling his memories. Yeah, so this is about volumetric processing with some examples. Now let's move ahead to volumetric video streaming. So one issue is that it's the rendering usually on is pretty complex. Yeah, depending on the resolution of the assets, the number of assets, and so on. So therefore, if you want to have mobile solutions, mobile applications, or lightweight applications, then you need to think about how to offload the rendering. And if we are able to do the rendering on a cloud server, for example, then we just need to transmit the 2D video stream of the current view, depending on the user's head pose. However, this requires a low latency system and network, and neighbor group worked on this and developed this edge cloud server, which uses the volumetric video file as an input, implemented some GStreamer modules and together with a Unity application, which does the animation or the rendering of the video. And this is then encoded and transmitted, and on the receiving side, then the user just sees the current 2D view, which is rendered. However, there's a back channel which transmits back the head pose and position and orientation of the head to provide the desired perspective onto the scene. And here is an example concerning the real-time capability. So on the screen in the back, you see the server and the mobile device in front. So we can move the volumetric assets. You see the assets are dynamic. Yeah, we can walk around and also see the volumetric assets from different perspectives. So here in this case, there is another feature embedded, which is head rotation animation. So the person is this basketball player is moving his head towards the user to follow the head gaze of the user. Yeah, so that's a quick presentation of volumetric streaming. And as already mentioned, we also are able to animate volumetric video. So it's not just having this sequence of meshes, but we can also modify the meshes and animate. Rotating the head, for example, is also pretty interesting. And again, for the use case of for the Holocaust survivors, it is it's a pretty interesting feature, because in our second production with Eva Umlauf, she was captured alone, and so therefore, if we put her in the VR scene, she is talking in some direction, yeah. And if you are somewhere positioned in the VR scene, usually she steers in some direction, yeah, where she was talking at. But in this scenario, you usually want to get in touch, get in contact with this person. So therefore, we modified the head orientation of this Holocaust survivor, looking towards you as a user, yeah? And this gives immediately a completely different impression, yeah, because you feel she is telling you her memories, she's telling you her story, and this makes this application pretty immersive. And but beside modifying meshes and of Holocaust survivors is should be avoided, just because of ethical reasons and so on. Yeah, we could also animate lips and let them talk different things, but this is a documentary and everything else is completely forbidden. Yeah. Yeah, so how does this work? We have our volumetric mesh on one hand. We have our human body model, which we fit to the mesh. And then we calculate a correspondence matrix between the model, which we can animate, and the mesh. And then we are able to animate this volumetric mesh interactively and change the mesh based on the underlying human body model. And this is presented here in this short video. So we capture our person. Here you see the mesh processing and the tracking, the registration, which leads to a much more stable mesh. Yeah, you see the keyframes where we have some topology changes, but in between it's pretty stable in the temporal sense. Then we generate the texture atlas. That's the UV map creation. And finally, we are able to we do the mesh registration, creating this, fitting this shape adaptive human model. Then we are able to modify the head orientation in any direction. So this can also be done, and this is the example of where the volumetric character is looking at the user. This can be done in real time on our high quality, high resolution volumetric video. Yeah, this luckily brings us to the top, to the outlook. And so therefore the question is what remains? So I have to say there are still a lot of challenges. So capture looks pretty complex, pretty expensive capture studios and so on. So we want to be mobile, we want to be portable, we want to have it cheaper. Perhaps we have too many cameras. We want to achieve the same quality, but using fewer cameras, or even with just one camera. Yeah, so perhaps with future AI algorithms, we are able to do so. AI is now entering the whole workflow, either on different modules in the pipeline, but also complete surface reconstruction based on images. So our colleagues are just only working on these new tools, and we completely leave out our original workflow. But also complex structures like hairs, reflective and transparent surfaces, and so on, is still a challenge, although new surface reconstruction rendering approaches can deal much better compared to standard vision-based 3D video processing. Then material properties is of interest for certain use cases. And finally, we want to have not only offline VR, AR applications, but we want to have real-time telepresence, video communication scenarios. So with point cloud-based approaches, this is already possible, but the quality is still poor. So therefore, for high quality real-time approaches, it is still a challenge. So therefore, though we have achieved a lot in the past 10 years in this topic, there's still many more to do, and that's the reason why I'm so enthusiastic in this topic. Yeah, so that's all about. Thanks for climbing with me on the volumetric mountain. Thanks for your attention. And yeah, it's not just my work. The whole department contribute to this research results. Thank you for your attention.
Thank you, Oliver. So, any questions from the audience?
Yeah.
Yes.
This is an area I'm also very interested in because I'm from School of Computing. Also did research in my PhD in volumetric video, and it's something I'm actively working right now. Can you talk a little bit more about the mesh compression? Because it works, it's like from the last video where you showed the different steps before getting the keyframe meshes, the next one works really well. And it doesn't require, you're not doing anything related to rigging or bone structure, right? So it's purely triangle based.
Yes.
Can you talk a little bit more
Yes,
about that?
yes. Well, there we So first we use Poisson surface reconstruction, to get the meshes, and then we do a little bit of mesh cleaning and also mesh reduction. So our modules are based on standard modules, but there are some slight modifications here and there.
I mean, the temporal aspect is the one I'm most.
Okay. Yeah. So for the temporal aspect, it's we define the keyframes, and the keyframes are defined in a way where we notice significant topology changes. And so if we have a range of frames where topology is almost the same, but just some small geometrical changes, we keep the topology and just modify the vertices, and this helps already a lot, because it becomes really temporally stable, and but still there are some, for example, if you touch your body and so on, these are the cases you need to exactly identify these parts where you have these topological changes. But that's pretty important step.
Any other questions?
Yes. I was wondering from your research, in terms of believability or the effects of the uncanny valley, what would have a greater effect? Either the meshes from being captured to being reduced down and smooth, which is its own subject in of itself, with some details inevitably lost, especially with pairing like fuzzier details. Is it that causes more effect of unrealism or uncanny valley, or say less realistic or harder or not quite real life lighting, like a human model under just, I mean, not what would be equivalent in this would be ray traced, like real life lighting.
Yeah, that's a good question, and I think it depends. Can a little bit overcome this uncanny valley with the right use case. For example, in this Holocaust survivor use case, you are so into the story, so that this realistic representation of this person supports your immersive experience, but you accept slight unrealistic modeling, some artifacts in lighting, inconsistent lighting, and so on, But to be honest, I cannot really say much about differences concerning ray tracing and so on. There is still the level of quality, at least with our approach, where we use this high resolution cameras, is pretty nice and pretty accurate, but still there are some artifacts noticeable.
Yes, I mean, it would be lovely to have the 1.5 terabyte model going live. It's like, oh, we see all the detail with computer could process that at real-time rate. Basically none. Be great, but no.
But I have to say the 1.5 terabyte is it's mainly because of this stereo setup, and a lot of information is irrelevant. It's just because of to serve our stereo approach. For this, if we move now to these multi-view surface reconstruction, AI-based surface reconstruction methods, we can we achieve the same quality with half the number of cameras. So, but still there is some significant overlap, some required overlap in between different views. And the challenge is to keep the necessary information and remove the unnecessary ones to reduce the overall data.
Yeah, fantastic. Again, Oliver, we're going to have to wrap up there. Oliver, sticking around. If you have some questions later on, there'll be time. But we'll wrap up this session and then we'll move on to the next one immediately afterwards. So thanks again, Oliver.